And this is this is the topic that we call parametric curves. If you take Calculus 3 next fall, you will see curves again. You're going to see two-dimensional curves and also three-dimensional curves. So curves in space, as well as surfaces in space and so on. But so we are going to be looking at curves which are called parametrized curves, and we also say these are curves defined by parametric equations. Now, so far in calculus, you have seen when we talked about curves, we usually meant graphs of functions, real valued functions of one variable. So that is, you look at functions like y is equal to f of x, and then the graph of such a function, this function is what? The input is a real number, the output is a real number. So for functions like this, we look at the graph of that function, and that's the type of curves we have seen so far. But we are looking at when we are talking about curves here, we mean something a little bit different. In order to sort of describe it in an intuitive way, I'm going to say the following. Suppose that there is a red bug, and the red bug is moving on the plane. So as the red bug is moving on the plane, it is tracing out its path, right? And I'm going to call its path the curve. Okay. So a bug is moving along a curve, which is its path, and it is tracing out a path, and that's the curve, and it's called the parametrized curve. Now, how would I describe the position of the bug? Well, at any moment t or any time t, I have to tell you what's the x coordinate of the bug and what's the y coordinate of the bug. So R of t is giving you the position of the bug at time t. So R of t, that's the position of the bug at time t. So R of t specifies the x coordinate and the y coordinate. Let's say at time a, when time is a, R of a is the left-hand point of the curve. When time is b, let's say the R of b is the right-hand point of the curve. Okay, so you can think of a curve as being the path of a moving object in the plane. Okay, the path of a moving object in the plane. And let's say here t is over some interval I. Okay, and now, mathematically, I wouldn't care about motion, or I wouldn't care about any applications. So mathematically, what is this curve? What's the mathematical definition of the curve? Well, mathematically, the curve is just a function. So mathematically, R of t, it's just a function, but it's not the types of it's not the usual functions you have seen so far. This function, the domain lies on the real line. So input is a real number. However, the output is a point in the plane. So you can think of R of t. Remember, R of t was x of t, y of t. So R of t is specifying the position of the bug. You can think of it mathematically as just a function. So given a point on the real number line as an input for the function, it gives you a point in the plane. So R2 is the plane, and R is the real number, right? So this is a one-dimensional space, and this is the two-dimensional space here. So your input lies in the one-dimensional space, your output lies in the two-dimensional space. Am I clear? So what is R of t? R of t is just a function that takes a point it takes a real number to a point in the plane. So this is so far all our functions were real valued, right? Meaning real valued functions means the output value is a real number. Now these are not real value. This is not a real valued function. This is a function where the outputs are points. Is that clear? In fact, I can think of the output as a vector. So at time t, right? At time t, R of t is this point here. Then I can think of this R of t as a vector where the tail is at the origin and the tip of the vector is at the point on the curve. So this point that I get here, I can also think of it as a vector. So I can think of R of t as a position vector. Am I making sense? So you start with R of a, that's a vector, and then it's tracing out the curve. So you can think of R of t as a vector as well, where the tail is at the origin. Is that okay? We are not going to be concerned with the vector view of this curve. You're going to do that in Calc 3. I'm going to say maybe a few more words on this, but not too much. Okay, so once again, let me emphasize that the domain of R of t consists of real numbers, while the range of R of t consists of points on the plane. Okay? So for us, what is a parametrized curve? A parametrized curve is any function out of t, where R of t is a point. So you can think of the point having two component functions. So the x coordinate function and the y coordinate function. So one application of a function like this is that you can think of a function like this as the position of a moving object, but that's not the only application. You can think of many other situations where you can use a function like this to describe something. Okay, but this view that R of t is giving you the position of a bug or something, it is a helpful way of thinking about it. Okay, and you will see why. Now, given a curve, right, there is this idea of orientation of the curve. So what's the orientation of a curve? Well, if you think of the curve as the position of a moving object, then you want to know how the bug is tracing the path. So in what direction is it tracing the curve? Okay, so how is the bug tracing its path? And that's called the orientation of the curve. Okay, how is the curve traced? So let's say, in my picture I used some arrows here, right? So by using the arrow, I'm telling you the bug is moving toward the right, and then it's making a loop here, and then it keeps going to the right and ends up at the point R of B. Okay, so that description is telling you what's the orientation of the curve. Again, the orientation means how the bug is tracing the curve. So the orientation for us means the description of how the curve is traced. Description of how the bug is tracing its path, or you can say the description of how the curve is traced as the parameter t is progressing, as the parameter t is progressing over the domain, how the curve is traced. And we're going to see how to determine that in an example in a bit.
Go back up to the domain range.
Yes. All I wanted to say there is that the domain consists of real numbers, but the range consists of points in the plane. Is the idea of orientation clear to you? We just want to describe how the curve is being traced as the parameter t is progressing. Okay? There are many ways of tracing the curve, right? For example, this is not the only possibility, right, of the orientation. Maybe at time A you are here instead of there, and you're tracing it the other way. Or maybe you're going to come to this point and then go there, and then come back, and then make a loop, and then go back. So there are many possibilities here. So the orientation, there are many possibilities of the orientation for the same curve, right? Okay. We are going to use a different notation for a curve. Instead of using r of t is equal to x of t comma y of t, we sometimes write c, so we are calling or naming the curve c, and then we are saying the curve c is determined by x and y, where x is x of t, y is y of t, and t is progressing over some interval I. So we specify the interval of values of t, and then x of t and y of t will be some formulas in terms of t. Okay? X of t will be a formula in t, y of t will be a formula in t. Okay, so let me write down right away an example. In my example, I am describing a curve. On the left hand side, I am saying r of t is x of t, y of t, and I am specifying the x coordinate in terms of t. The x coordinate is given by t squared minus 2t. The y coordinate is given by t plus 1. For a given value of t, those are the coordinates. And the interval of values of t is the entire real line. So t is from negative infinity to positive infinity. T progresses over negative infinity to positive infinity. And the other notation for a curve, I'm going to say, well, let's call the curve c, and x is t squared minus 2t, y is t plus 1, and again, you have to specify the interval of values for t. Okay, so that's the curve that I'm defining, and I gave you the formulas for the x and y coordinates. Given the definition of the curve, we want to know how we can sketch, how we can come up with the plot of the curve, and then we need to know how we can determine the orientation of the curve. Okay? Is it clear? So let's. So that's the problem. Everybody's clear what the problem is? You are given a curve. The coordinates are specified by the functions t squared minus 2t and t plus 1. Now, how would you plot the curve? Well, first of all, let's try to think about how a computer will do it. So how will a computer come up with the plot? Well, the computer will do the following, right? It's going to basically it's going to pick certain values for t, maybe 100 values of t or 1,000 values of t, right? And then it's going to compute corresponding values of x and y. So let's pick t to be -2, -1, 0, 1, 2, 3, 4, and then let's compute x. Remember, x is what? T squared minus 2t. Y is p plus 1. So when t is -2, what is x? Well, you're going to plug in -2 where? You're going to plug in -2 for t. You get -2 squared minus 2 times -2, right? And you get 8. If you plug in -2 here, you get -1. So you plug in different values of t in x and y, and you compute corresponding values of x and y. And those are the values that you get. Okay, so again, the computer will pick bunch of values of t and then evaluate the corresponding points on the curve. So how many points do I have here? I got the point 8, -1. I got the point 3, 0. I got the point 0, 1. I got the point -1, 2. I got the point 0, 3, 3, 4, 8, 5. Right? Those are the points that I get. Those points lie on the curve. So then I'm going to plot, the computer will plot them on the plane. So I have plotted those for you, all the pink points that I have. When t is -2, when t is -2, you get the point 8, -1, right? So that's the point 8, -1. When t is -1, you get the point 3, 0. When t is -1, you get the point 3, 0. When t is 0, you get the point 0, 1. When t is 1, you get the point -1, 2. When t is 2, you get the point, what is that point? When t is 2, you get the point 0, 3. And then when t is 3, you get the point, what is that, 4, 3? No, 3, 4, 3, 4. And then when t is 4, you get the point 8, 5. Yeah.
So we're putting these t values into a new function and getting x
Not-
and y values?
Not a new function. This x and y were given in the problem, right? X was given to the t squared minus 2t. Y is given to the t plus 1. So for each value of t, I'm computing the values of x and the value of y, and it's giving me pairs, right? It gives me pairs of points on the curve, and I'm plotting these points. Okay, I am labeling the points with t, right? But t is not. This is the x. This is the xy plane. That's the xy plane, and I'm plotting those points that I got for each value of t. So for each value of t, you get a point. You're plotting that point. Okay, and once you plot enough many points, you see what the curve is. And in this case, you can probably already imagine. At the beginning of the class, I said you guys are trying to make a parabola. In this case, we have a parabola. Okay? It looks like if I look at the points, they are forming a parabola which is opening to the right. Is everybody clear?
We're getting 2 points or a point from 2 different functions. The x and y.
Yes. Yeah. Remember, x is specifying the x coordinate. Y is specifying the y coordinate. Right? The function y is specifying the y coordinate. So there are, the function, the curve is being specified. The curve is being specified this way, right? X is t squared minus 2t. Y is t plus 1, right? So for each value of t, so t is the parameter here. So for each value of t, think of t as time, and x and y is specifying the coordinate of a moving object. So at time, when t is time -2, you get a point, you get a position. When t is -1, at -1 time, then you get a position. When t is 0, you get a position. When t is 1, you get a position and so on. So you can think of 0 being the current reference time. Before that, those are the past times. After that, those are the coming times. And so you get these points and you plot them, you see what the curve is or what the trace of the moving object is. If you're thinking of this as if you're thinking of the C as being the position of the moving object. Is that making sense? Okay, so that's how a computer will do it. But we are not computers, so let's see how we should be doing it. So this is how we are going to do it. We are going to see if we can. We can eliminate the parameter t. We will try to see if we can eliminate the parameter t and obtain a relationship between x and y. Am I making sense? Between the component functions, is there a relationship between the variable x and y? X depends on t, y depends on t. Can I come up with an equation involving x and y, getting rid of t? If I can, what is that going to tell me? So suppose that I eliminate t somehow, and I find that x and y, remember for each value of t, you get a value of x and y. Let's say I show that x and y satisfy an equation. So this is some equation involving x and y. So I'm assuming that somehow I got rid of t, and x and y functions, the component functions, x and y, they satisfy an equation involving them. So what does it tell you? What it tells you is that any given point on the curve, right, any given point on the curve will satisfy this equation, right? Any given point on my curve, on my parametric curve, will satisfy this equation. Is that making sense? So let's think about again that. Remember, I have x is given to be t squared minus 2t. Y is given to be t plus 1. Right? That's the curve. Right? That's the parametric curve. Now, suppose that somehow I got rid of t and I obtained some equation involving x and y. So what does it tell me? What it tells me is that any point that I obtained for my curve, any point that lies on my parametric curve, what does it mean I have a point on the parametric? It means that for some value of t I get that point. If I say a point lies on my parametric curve, it means that there is a value of t for which I get that point, right? And that point will satisfy this equation that I obtained, right? So any point on my parametric curve will satisfy the equation, right? What would that tell you? What it tells you is that whatever the graph of the equation is, the curve, the parametric curve, will be part of the graph of the equation. Am I making sense? All I'm saying that every point on my curve satisfies the equation. Every point on my parametric curve satisfies the equation. The implication of that would be that my curve will be part of the graph of the equation, right? So you have you have your curve, parametric curve, you have the graph of the equation that you obtain. What's the relationship? Well, the curve must be part of the graph of the equation. Did that make sense? Okay, so once I get the equation, then I know that the curve C must be a part of the graph of the equation. And well, let's do that. So let's do that for our example. In our example, what is x? In our example, x is t squared minus 2t, and y is t plus 1. I want to somehow get rid of t and find an equation involving x and y. How may I do it? How can you come up with an equation involving x and y only? Very good. So you get t equals to y minus 1, and then I'm going to plug that in here. So I get x to be y minus 1 squared minus 2 times y minus 1. Right? And I obtain an equation involving x and y only. Hopefully this equation would be a familiar equation that I know how to sketch the graph for. So this would be equal to what? Let's simplify this. You're going to multiply out y squared minus y minus 1 squared. So what is that? Y squared minus 2y plus 1. So you get minus 2y plus 2 from the second parenthesis. And then if you simplify that, you get y squared minus 4y, what is that, plus 3. So what I get then is that x is y squared minus 4y plus 3. So if I know the graph of that equation, I know that the curve C must be part of the graph of that equation. Okay, now what's the graph of this equation? How can I come up with the graph of that equation? Well, I mean, I just want to recognize whether it's a familiar equation or not, okay? Instead of plotting points. So, what is that? This is, if I complete the square for the quadratic on the right-hand side, what am I going to get? I'm going to get y minus 2 squared minus 1. I showed you how to complete the square before, so I'm not going to do it here, but if you complete the square, you will see that you get y minus 2 squared minus 1. Don't worry about how you obtain that right now. Just complete the square, that's what you get. And so what then I have is that x is equal to y minus 2 squared minus 1. Okay, now if I change the role of x and y, you know exactly what's going on, right? If I change the role of x and y, you know that I get what? I'm just saying that what's the graph? So suppose I have y is x minus 2 squared minus 1. Do I know what the graph is? It's a parabola opening upward with vertex given by this and this. But now, it's x equals to that. So x is a function of that, right? So it's going to be a parabola opening to the right. What would be the vertex? What will be the vertex? So this is a parabola that opens to the right. Negative 1, 2. Very good. So the vertex would be negative 1, 2. Okay? So just think of x as a function of y, switch the role of x and y, and imagine what's going to happen. And then, so we get a parabola that opens to the right with vertex at negative 1, 2. Is that what we had? Yes. When we plotted the points, we recognized that. So I see that. Let me just complete the graph here. And then so the parabola opens to the right, but one thing to understand here that it is going upward forever and to the right forever, right? And the other part, the lower part, is going downward forever and to the right forever, right? So okay, so that's the graph of that equation. So far what do I know? So far I know from my work when I eliminated the parameter t and came up with an equation between x and y, and then I sketched the graph of the equation, what it tells me is that the curve that I have, every point on the curve satisfies the equation of the parabola. So when I eliminate the parameter t, it only tells me every point on the curve satisfies this equation, which means every point on the curve is on the parabola. So all I know is that my parametric curve is part of the parabola. That's all I know. My curve is part of the parabola. That's all I know. My curve lies on the parabola. Right? Now there are two questions to be asked. Is my curve the entire parabola? I know that it's part of the parabola. Is it the entire parabola? Two, is what's the orientation? What's the orientation? So when I'm talking about the orientation, I'm asking, how is this curve traced out? As t is progressing from negative infinity to positive infinity. As t is progressing, how is this curve traced? Am I coming this way or am I going this way? Am I making sense? So what's the orientation? Is it like this, or maybe it is like this? How is it traced? If you think of it as if you are thinking of it as the trace of a moving object, how is the object moving? Is it moving from below and it is going up and left and then going up and right, or is it the opposite way? Okay, and we are going to take help from Calc 1 to do that. So the step 2 would be draw the graph of the equation that you obtain after eliminating t, which we have done, and then step 3 would be to determine the orientation of the curve and whether my curve is the entire graph of the equation. Let me give you a few seconds to write that up. Okay, determining the orientation is not hard. It's pretty easy. We just need a little bit of help from Calc 1. You're probably done with number 2. Whoa. Okay, are you done with number 3, step 3? Okay, so now let's think about how I can come up with the orientation. All you have to do, you have the component functions for the curve x and y, right? X and y. Just determine the behavior of x and y in terms of how they are increasing and decreasing. Can we do that? Well, we learned it from Calc 1, right? How is the function x? How is the x coordinate increasing and decreasing? And how is the y coordinate increasing and decreasing as t progresses? Am I clear? How is the x coordinate increasing and decreasing as a function of time and t, and how is y coordinate increasing and decreasing as a function of time? Now notice these are very simple functions, right? X is t squared minus 2t. So what is the derivative of x? The derivative of x would be 2t minus 2. And then what's the critical point? What's the critical point? Where is the derivative 0? The derivative is 0 exactly when t is 1. Okay? So now I have to know where the derivative is negative and positive. Well, when t is 0, you get negative. So on the left side of 1, the derivative is negative. When t is 2, the derivative is positive. So you know that on the right side of 1, the derivative is positive. Right? Look at the derivative of x. Look at where the derivative is 0, or find the critical point, plug them, and then figure out where the derivative is negative and positive, and then that's going to tell you where x is increasing and decreasing. Right? We have done that in Calc. Okay, right at 1, what's the value of x? Right at 1, the value of x is what? Well, I can compute, right? X is when t is 1, x is 1 minus 2, which is negative 1, right? So right at 1, x is negative 1, right? Is 1 okay? Right at 1, x is negative 1. Now let's figure out. I know that x is decreasing and then increasing. But I need to figure out where is it decreasing from? Where is it coming from? Is it coming from 5 feet above, or 6 feet above, or is it coming from infinity? Okay. So, how do I determine that? Well, think about when x is negative and large. So when t is negative and large. When t is negative and large, what can you say about x? When t is negative and large, t squared is going to dominate 2t, right? So when t is large and negative, t squared is large and positive, right? So I know that x would be large and positive. When t is negative and large, x is positive and large. Right? So I know that it's decreasing from positive infinity. Now, is it increasing toward infinity? Well, let's think about this. When t is positive and large, x is positive and large, right? So I know that x is going to infinity. So what's happening then? As t progresses from negative infinity to positive infinity, x is decreasing from infinity to negative 1, and then x is increasing from negative 1 to infinity. Right? Well, we do the same thing for y, but y is actually easy. Y is t plus 1. As a function of t, y is linear, right? So it's just a line, right? So I know that if you look at the derivative of y, it's just 1. So you know that the derivative is always positive. It tells you that the function y is always increasing, right? Because the derivative is always positive. Now I have to think about how is it increasing. When t is negative and large, y is negative and large. So it's coming from negative infinity. And when t is large and positive, so is y. So I know that y is coming from, so the y is increasing, and it is increasing from negative infinity to positive infinity, right? It's always increasing. Is everybody okay? So as t progresses from negative infinity to positive infinity, y is increasing from negative infinity to positive infinity. Once I know that, let me write that down. As t progresses from negative infinity to negative 1, x is decreasing from infinity to negative 1, y is increasing from negative infinity to 2. Okay? And then as t progresses from 1 to infinity, x is progressing from negative 1 to infinity, y is progressing from 2 to infinity. That's the recap of what we did. And then we're going to apply that to come up with the orientation, okay? Is everybody okay? So let's go back to our curve, our parabola, and did you guys need time to write that down? Go ahead and write that down. And if you have already written it down, think about the parabola and see see if you can come up with the orientation now. So remember, we are breaking up time. Let's think of this as time versus and the curve is the path of the moving object. We are breaking the time at what? -1, right? Was it -1? Were we breaking time at -1? No, sorry, at 1, right? We are breaking time at 1. This number was 1. This number was 1. So I had a slight mistake there. Okay. Now let's figure out what is it telling me then. Since we are breaking up time at 1, what is happening at time 1? Where am I? At time 1, I am right here. Right? At time 1, I'm at the vertex. Now think about this. As time progresses from -infinity to 1. As time progresses from -infinity to 1. What is happening to x? X is coming from infinity and decreasing to -1. Right? Remember that? X is coming from infinity and it is decreasing up to -1, right? And then X starts to increase from -1, right? After time 1, X starts to go from -1 to positive infinity again, right? So what's happening? X is going to -1 and then it's going back to infinity, right? So how should the curve be traced? Like this, it's coming here and then it's going up. Remember what is happening to Y? What is happening to Y? Y is always increasing from -infinity to positive infinity, right? So Y coming from -infinity, right, below, right, and then it's going to positive infinity, right? Y is going from -infinity to positive infinity as t progresses. So if you put them together, you see that the curve must be traced out this way. So the curve must be traced out. The curve must be traced out this way, right? Because as t progresses, you know that x is coming from infinity to -1, and then it's going from -1 to infinity. Y is always y keeps increasing, so y goes from infinity to positive infinity, which you can see. So that's the only possibility for the orientation. Now, at the same time, we actually can answer now whether the curve is the entire parabola. The answer is yes, right? Because as t progresses from -infinity to positive infinity, what is happening to x? X is coming from infinity to -1, and it's going from -1 to infinity. So you are actually getting all the points on the parabola. You're not missing any of the points. Did that make sense? Okay, so that's how we know that. Any questions? So my final answer is what? My final answer is the curve is the entire parabola and the orientation is given by that arrow. In fact, I already answered the orientation when I wrote down this. When I wrote down this, I already answered orientation. Okay. We are almost out of time, so I just want to say a couple of things here. The next thing that I need to do is go over 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 more examples that I'm going to go over tomorrow. But those examples would be much quicker than this one. This one I took a lot of time. and those are actually easy as well. But one thing that I want to allude to you also is that some of the important things we want to know about the curve is that what's the slope of the curve at a given point. So I want to know, given a point like this, say, what's the slope of the tangent there? Okay? Why is it important to know the slope? Because it tells you something about, if you think of this as the path of a moving object, right? I mean, I'm saying it's the path of a bug, but maybe I'm thinking about the path of a satellite or something else. You want to know, that's going to tell you the direction, right? The direction, the slope is going to indicate what's the direction of motion at that point. Now, another thing that I want to mention here, so we're going to talk about how to find the slope. But one more thing that I want to say here, for those of you who's going to take Calc 3, is that if you think of this as the position of a moving object, then one thing you want to ask is that, hey, what's the velocity of the object, right? What do you think the velocity is? So at time t, let's say this is the position at time t, right? That's the position at time t. At time t, what would be the velocity? Well, if the object is moving in this direction, then the velocity would be tangent to the path, right? At that point, that's the direction of movement. So the velocity would be given by the tangent vector. In fact, how would you get the velocity vector? The velocity vector would be, you have the component function x and y, you just take the derivative of each. And you're going to get derivative of x, derivative of y. That's going to be your velocity vector at time t. And that's going to be the tangent vector. Okay? Now, the direction of the vector tells you what? The direction of motion at that time. The length of the vector tells you what? The speed at that time. The speed at that time is the length of the vector. Okay? Now here's the thing. What if you have a path of a moving object, you want to know what's the total distance covered by the object, right? I want to know what's the total distance covered by the object. What would be the total distance? How would you find the total distance? You're going to integrate the speed function. You're going to integrate the speed function. You're going to obtain the total distance, for example. Okay? Now, of course, motion for us, when we talk about the motion of a satellite or something else, we are not looking at only two-dimensional movement, right? We are looking at three-dimensional movement, right? So what movement in space? In that case, you do very similar stuff. Okay? Now, we're not going to really talk about those type of things probably much. You're going to see that in Calc 3.